Lesson 12.10 picks up where we left off from last section. In the previous section, we were developing power series primarily from the geometric series with the functions 1 over 1 minus x and 1 over 1 plus x. But today we're going to go in a very different direction. We're actually going to look at question 1. If a function is equal to the summation from n to 0 of a sub n to x sub n, and by the way, we'd say this is centered at x equals 0, or f of x is equal to sigma of a sub n x minus c raised to the n, this would be centered at c. And by the way, whatever you are seeing in these parentheses, x minus c, that's where you will find your center. You can see for the first example that would be equivalent to x minus 0. What would that form of a sub n really look like? Well, this theorem right here is just amazing. It's saying, let's say that f has a power series, but you don't know what it looks like. You have a radius of convergence r. Again, this is centered at x equals 0. Whenever we're centered at x equals 0, we're going to call this a Maclaurin series, saying that our function will equal this power series. What would a sub n look like? Well, amazingly, a sub n will be the nth derivative of your function evaluated at 0 divided by n factorial. And this is just really remarkable. I hope you can see here f of x equals this power series, but look at what is in front of each power of x. Let's look at, say, x sub 2. What is the coefficient of x sub 2? Well, it's the second derivative of f evaluated at 0. Remember, we're centered at 0 here, divided by 2 factorial. Notice the 2's. We have the second power, the second derivative, the second factorial. Look over here for x to the 1. This would be x to the first power, of course, first derivative, and 1 factorial would be underneath here. Similarly, we could say, well, what about x to the 0? Well, with x to the 0, we take the 0th derivative, the function itself, evaluated at 0, divided by 0 factorial. Even in that first term, you can see this is the case. But what we were pointing out earlier is that for any term here, for the x to the n term, the coefficient is the nth derivative evaluated at 0 divided by n factorial. Notice what this is really saying. We can evaluate, we can work out what the power series representation is for a function if we'd like for that to be centered at 0. Now, very similarly, if f has a power series representation centered at x equals c, well, that would be called a Taylor series. And the Taylor series you're going to see is remarkably close to the Maclaurin series. In fact, the Maclaurin series is actually a special case of the Taylor series. Once again, notice that if you wanted to find the coefficient a sub n out in front of x minus c raised to the n power, what you are going to see here, again, is you will have the nth derivative of your function evaluated at c divided by n factorial. Again, let's just say look at the second power. If you had x minus c to the second power in this power series, the coefficient out in front of it would be the second derivative evaluated at c, remember we're centered at c, divided by 2 factorial. And just as a word, sometimes we might be wondering, what exactly do you mean that we are centered at C? You might remember in our previous section, at least in class, I was using the graphing calculator to show how this power series would converge to the function. Well, the center would be the actual point of contact with the graph, and moving to the right and the left would be your radius of convergence. So we can even take a look at that in the next few days in more detail. But let's develop a Maclaurin series for e to the x. Now, a Maclaurin series, of course, is centered at 0. So tell you what we're going to do. Let's just look at f of x, which of course is equal to e to the x. Remember, we're centered at 0, so we're going to evaluate at 0. E to the 0 power is a 1. We could say, well, what if we'd like to take our first derivative? Well, my goodness, this is wonderful. The derivative of e to the x is still e to the x. And then f prime of 0, very simply, is 1. E to the 0 is a 1. It doesn't take too long for kids to notice very, very quickly that the second derivative and all derivatives, in fact, will be e to the x. And in fact, any derivative evaluated at 0 will always be 1. Now, we could even look above up here with the Taylor series, just realizing that we are centered at 0. We could say, well, my goodness, e to the x is going to be f of 0 plus f prime of 0 times, well, x minus 0 to the 1. And technically, we're dividing by 1 factorial as well. You could say then we need the second derivative evaluated at 0. Here's x to the second, divide by 2 factorial. We take the third derivative evaluated at 0. Here's x to the third, divided by 3 factorial. We could say, hey, let's keep going just a little bit. And we could say, well, what about the nth derivative? Well, the nth derivative evaluated at 0 we could actually figure out as well. Here's x to the n divided by n factorial. Well, it won't take you very long to see, thank goodness, that f of 0 is a 1. F prime of 0 is a 1. So is f double prime, f triple prime, all of these. So I'll just have x all over 1 factorial. Here I'll have x squared all over 2 factorial, x cubed all over 3 factorial, x to the fourth all over 4 factorial if we wanted the next one. Here's x to the n all over n factorial. And unbelievably, we could even write this as a sigma. We could say, well, wow, just looking at that nth term, we know that we'd have x to the n all over n factorial. We'd like to begin at 0. Remember, we had our 0th derivative and so forth. It would only take a moment to double check that this, in fact, is your series. Unbelievably, we have just found the power series for e to the x. How wonderful is that? Well, let's continue on and just briefly say, well, what about the radius of convergence and the interval of convergence? I do want to talk about the ratio test here. Let's look again at this nth term and say, do you know what? The ratio test was such a nice, easy way to work this out. The limit is n goes to infinity of the n plus 1 term divided by the nth term. My goodness, remember there are x's in here now as well. So this is going to be x to the n plus 1 over n plus 1 factorial. Rather than divide, let's multiply by the reciprocal. And real quickly, we know that n plus 1 factorial is n plus 1 times n factorial. These n factorials cancel out. X to the n cancels with x to the n plus 1, leaving you with an x. And all of a sudden you see something maybe a little surprising. Up here you have an x. Down here you have n plus 1. But as n goes to infinity, this must go to 0, less than 1. This converges for all real numbers. My goodness, the interval of convergence is all real numbers. So, unbelievably, this e to the x is a little bit surprising. It's unlike our previous section we see convergence for any x value that we would like. Wow, let's keep going. Question number 2. Well, rather than even address this question, how do we know that this exists? We're not going to really address that in our course. But we are going to look at a Taylor polynomial. If you want to have an nth degree polynomial to approximate your polynomial, you would just have to go up to this nth term, and the coefficients, as always, would be the nth derivative of the function evaluated wherever you're centered, divided by n factorial. Real quickly, I do want to just briefly talk about your error. Your error, if you were to make an approximation, would be found by something called the Lagrange error bound. That's honestly our next and last lesson of chapter 12. It's just an introduction here. All I want to point out, and we're definitely going to talk about this in our next lesson, is just as in the alternating series for the error approximation, you found that the n plus 1 term would measure the error for the nth sum. Well, again, if you were going up to the nth polynomial, notice how our error would be one step beyond that at the n plus 1 derivative evaluated at z. We'll talk about that later. But definitely just wanted to introduce this and also make a comment that when we do have Taylor series representations, this Lagrange error bound will approach 0 as n approaches infinity. So, tell you what, for example 2, find a Maclaurin series for sine of x. Let's see if we could do this very, very fast. First of all, f of x is equal to sine of x. Remember, we are centered at 0. F sub 0, sine of 0 is 0. We could say, well, let's take a derivative, first derivative. The first derivative of sine is cosine. Now remember, the evaluation of cosine of 0 is a 1. Let's take our second derivative. The derivative of cosine is negative sine of x. If we were to substitute in a 0, we'd be back at 0. And then we could say, well, let's take a third derivative. Well, the third derivative of x, the derivative of sine is cosine, so we'd get negative cosine of x. And continuing on, if we were to plug in a 0, you'd see that we get negative 1. Once we take this derivative, I hope you notice very quickly that we have arrived at our original function, the sine of x. We're back with the original 0th derivative, if you would. The derivatives of sine functions are cyclical. They begin to repeat this pattern, and you can see that this pattern or cycle would be 4 steps long. So what we're going to do very, very quickly is just say that the sine of x would be, of course, with a Maclaurin series. We'd say, well, that's f of 0 plus f prime of 0 divided by 1 factorial times x to the 1 plus f double prime of 0, x squared all over 2 factorial plus f triple prime of 0 all over 3 factorial times x cubed. And then we'd say plus the fourth derivative, evaluated at 0, x to the 4th, all over 4 factorial. Well, it doesn't take long to see that actually we're going to have a 1 here, a negative 1 here, a 0, a 0. In fact, if you look very closely, all of the even derivatives are going to be 0. And that leaves us with an x plus x cubed all over, a minus x cubed. So sorry about that. Like I said, a minus 1's over here. Continuing the pattern, you might realize that we're just going to continue to alternate signs. And I meant to write a factorial down below. X cubed all over 3 factorial plus x to the 5th all over 5 factorial minus x to the 7th all over 7 factorial